Hello everyone. So today we're going to continue on talk about partial fraction decomposition in 11.5. So last video we get to go over one example where we have a repeated linear factor. So want to go through a few more examples with you before we try to talk about how to solve for the function y with all this new partial fraction that we haven't seen before. Because remember, we know how to deal with linear factor like this. But when we have a repeated linear factor, we actually don't know what function, when we apply Laplace transform, will actually give me that. So that would be something that we have to figure out later on. But I do want to go over more example of partial fraction decomposition first. So let's try a few more examples. How about this one? Okay, let's try to form the partial fraction decomposition for this fraction right here. Okay, so this one has a repeated linear factor, and this time the linear factor is x plus 3, but it's to the third power. Because it's to the third power, therefore indicate that we have to have 3 partial fraction in order to form this fraction correctly. So therefore, those are the 3 partial fractions that we have: a over x plus 3 plus b over x plus 3 square plus c over x plus 3 to the third. Okay, remember, these 3 partial fractions cannot have the same denominator, because if they do, they just form one single fraction. Okay, and therefore would not form 3 different partial fractions, and that screw up the process. So now what do we do with this? So, well, once again, just like how we did before, we're going to focus on the numerator. So the numerator will be 9x plus 25 will equal to a times x plus 3 square, because I only have x plus 3 on the bottom, but need to get to x plus 3 to the third, plus b times x plus 3 plus c times nothing in this case, because it actually has the entire x plus 3 already. Okay, so now comes the question of, then what do we do with this now? Well, we do the same thing we did before. We're going to start by letting x equal to some number that will help us solve this problem. So I'm going to let x equal to -3. And when we do that, I would have 9 times -3, which is -27, plus 25, which is -2, is equal to, a will go away because x plus 3, when I plug in -3, that becomes 0. And b would also go away, therefore just leave it with c. So therefore we know c must equal to -2. So that's good. Now the problem is, what are we going to do with a and b? Notice that there's no other x value that we can plug in that can achieve the same exact effect, because in this case, even though we have 3 partial fractions, we only have one single linear factor that repeated 3 times. And therefore, there's only one x value that can do what we just did. So what do we do with the other 2? Well, we can just pick other random numbers. And yes, just like what I told you last video, you can pretty much pick any number that you like, as complicated or as simple as you want. And of course, I would recommend go with simple. So here I'm going to pick probably one of the most easiest number to plug in, which is 0. So when I do that, what I have would be 25 equal to 9a plus 3b plus c, but since we know what c is, I'm going to put down c, which is -2. Therefore, result in this equation, 27 equal to 9a plus 3b, or if I reduce it further, 9 equal to 3a plus b. Notice that that wind up with an equation that involves a and b together, which is okay, because we're going to do this process another time, which will get another equation to relate a and b together, and hopefully using these 2 equations we can figure out the answers. So what should my next number be? So next easiest number to plug in would be 1. So I'm going to put in 1. Then 9 plus 25 is 34, equal to 16a plus 4b minus 2. So therefore become 36 equal to 16a plus 4b. And if I reduce again, that become, if I divide everything by 4, I have 9 equal to 4a plus b. So that's my second equation. Now all I have to do is use these two equations to solve for a and b. So if I look at this correctly, if I simply add the two equations together, or well, not add the equation, but multiply the first one by negative, and then add the second equation, I realize that these two cancel out. I have a equal to 0. And if a is equal to 0, therefore imply that b must be 9 in order for that to work. And so therefore now we have our answer. 9x plus 25 over x plus 3 to the third is actually equal to 0. So that's gone. B is 9, so become 9 over x plus 3 squared. And then c is negative 2, so minus 2 over x plus 3 to the third. And that becomes my partial fraction decomposition. Now we haven't tried a quadratic factor, so let's do a quadratic factor together. Let's see. So let's try this one. 8x squared minus 12 over x times x squared plus 2x minus 6. So notice that x squared plus 2x minus 6 cannot be factored because the only two pair of numbers that multiply to give you 6 will be either 1 and 6 or 2 and 3. Neither of those two would add or subtract to 2 in the middle. So therefore this will result in some kind of irrational roots on the bottom. And no, I do not recommend that you put two linear factors that have irrational roots, irrational number inside, because that just complicates the math by a lot. So you don't want to do that. So leave that irreducible quadratic factor. So this will break down into the following. So first it will be break down into a over x. That's my linear factor, which is x. Plus, remember, a quadratic factor actually form two things on top. In this case, bx plus c. Okay? So, therefore, the numerator will be x squared minus 12 would equal to a times x squared plus 2x minus 6 plus bx plus c multiplied by x. So this one is tough, but it's not undoable. Notice the problem here is that we only have one good x value once again, and that will be 0, because that will make bx plus c go away and allow us to solve for solve for a. But then to solve for b and c will require a little bit of work. So let's see if we can figure this out. So I'm going to let x equal to 0. And when I do that, I have negative 12 is equal to a times negative 6 plus b times 0 plus c times 0, which basically just go to 0. So therefore, I'm going to go and erase that. And that just tells me that a is equal to 2. So that's good. We found one of the three things we need. Now, next thing I need is to find b and c. Once again, there's no good x value that will work now because we take the only number that will work, which is 0, that will cause x to go to 0. But because this is an irreducible quadratic factor, meaning that whatever x value we choose that will make this equal to 0 would have to be imaginary or irrational. Both of them are not preferable for me to plug in. That would just make the math way more complicated. So I'm going to go and go for the next best thing. I'm going to go and pick two numbers that I like. I'm going to pick 1. So therefore become 8 minus 12, which is negative 4, is equal to, remember we all know a is 2. So I'm going to put 2 in. And then when I plug in 1, it becomes 1 plus 2 minus 6, which is negative 3. Plus 1 times b, which is b, plus c, multiplied by 1. And so this result in an equation b plus c equal to 2. So just like the last example, we wound up with an equation that involves the remaining two unknown coefficients, which is okay because we now form another equation. So what's the next number that we can use? So I'm going to do, it's really up to you. I can do -1, which is also relatively easy. But if you don't like negative number, we can definitely do a positive number like 2 maybe. How about we do 2? We can do 2. So therefore 8 times 2 squared, which is 4. So 8 times 4 is 32. 32 minus 12 is 20. Is equal to 2 multiplied by 2 squared is 4. 4 plus 4 is 8. 8 minus 6 is 2. Plus 2b times 2 plus c all multiplied by 2. So look at this right here. That would mean that's 4b plus 2c is equal to 16. And this equation can definitely be reduced. I'm going to reduce that. That will become 2b plus c equal to 8. So now just a matter of trying to figure out the solution to this. So I'm going to multiply the first equation by -1. And we'll keep the second equation. I'm going to add them together. So c cancel out. And I have b equal to 6. If b is equal to 6, then it seems to me that c must equal to -4. So 6 minus 4 is 2, and 2 times 6 minus 4 is 8. So that works out. So therefore, tell me that our partial fraction for this partial fraction decomposition for this fraction is equal to a, which is 2, so 2 over x plus 6x minus 4 over x squared plus 2x minus 6. All right. So what happens if we have a what happens if we have a repeated quadratic factor? So that's probably one of the more complicated partial fraction decomposition we have to do. So let's do one, just so that we can see how that works. So this is probably the last partial fraction decomposition that I want to do, and then we're going to have to talk about something else. Okay? So that's my fractions. Notice that the bottom is x squared plus 2 squared, so therefore we result in x to the 4th. And the top is a 3rd degree, so therefore it's still a proper rational function. Just like this one here, top is 2, bottom is 3. And this one, top is 1, the bottom is 3. So remember, you can only do partial fraction decomposition when you have a proper rational function. So what would be the partial fraction for this one? Well, it would be this. It's ax plus b over x squared plus 2 plus, I'm going to say cx plus d over x squared plus 2 squared. If you want to do a1x plus b1 and a2x plus b2, you can. I would just prefer not to have the subscript and just use different letter. And since we're not probably unlikely that we're going to, I hope, unlikely that we're going to run out of letters to you on the top. So I'm just going to go with different letters. And I usually use capital letter, but if you want to use lowercase letter, you can. Okay. So now just a matter of solving this. So how do I do this? So this is what we do. It would be 3x to the 3rd plus 7x minus 4 would equal to ax plus b times x squared plus 2 plus cx plus d. And multiply by nothing because they already have the common denominator. So once again, this becomes a major issue. The reason why it's an issue, because we really don't know what number to plug in. Okay? Because there's no really good number that will make the denominator equal 0. So what we're going to do is we're going to have no choice but to go for solving for these 4 things kind of manually. Okay? So what we're going to do is this. We're going to go and try to do the following. So what we can do right now is to basically let x equal to 4 different numbers and then try to solve for A, B, C, and D. And that will result in a system of 4 equation, 4 variables. And I'm not too keen into solving a system of 4 equation, 4 variable, which definitely can be doable, but it just seems like it might be a little hard to do. So I'm going to take a little different approach here, which is also a very valid way to solve this equation for A, B, C, and D. And as a matter of fact, I'm not sure Mr. Ambrose might have also showed you how to do this too. So what I'm going to do is the following. I'm going to leave the 3x to the third plus 7x minus 4. And what I'm going to do is simply multiply out the other side right here. So therefore become ax to the third plus bx squared plus 2ax plus 2b plus cx plus d. And what I'm going to do is try to now pay up the coefficient properly. So on the left-hand side, I'm going to say, well, this is 3x to the third plus 0x squared plus 7x minus 4. Well, on the right-hand side, I do have ax to the third plus bx squared plus, notice that for x, we have 2a plus c for x, and then we have 2b plus d for the constant. And now I can say, well, that coefficient must match this coefficient. This coefficient must match this coefficient. This coefficient must match this coefficient. And this coefficient must match this coefficient. And therefore result in a system of 4 equations. Okay, granted, this is the same as before, but this system is a lot easier to do because automatically I know that A has to be 3, B have to be 0, and then 2A plus C must equal to 7, and 2B plus D must equal to -4. So knowing A is equal to 0, C must equal to 1, and knowing B is equal to 0, D must equal to -4. And therefore give us the answer almost immediately. And now I can form my partial fraction. 3x squared, 3x to the third. Okay, I did miss right. 3x to the third plus 7x minus 4 over x squared plus 2 squared would equal to 3x over x plus 2 plus 1x minus 4 over x plus 2 squared. So that's my partial fraction decomposition. Oops. That's my partial fraction decomposition. So this one a little tricky to do, require a little bit different technique. If you want to go through the same process like we did here by picking 4 different values, you could, but it's just that you run out of good value to plug in because you can only choose 0, 1, you can only choose 1 ones, and you can choose a -1. But those are 3 good numbers, and then you will have to do some other numbers. And in this case, because there's C, A, B, C, and D, 4 different values that you have to look for, you're going to have to pick 4 numbers to do that. So I would say in that case, this method actually worked out quite nicely. And as a matter of fact, this method will work with all these examples right here also. It's just that for these examples, it's probably easier to just plug in a number instead of trying to multiply everything out and collect all the coefficient. Okay? I would strongly recommend that you don't use this method unless you have repeated factor. Because if you have non-repeated factor or no quadratic factor either, it should be relatively easy to just plug numbers in and figure out the solution. Alright? So now the last thing I want to talk to you about would be the following. Would be a table of Laplace Transform. So I actually posted that table in Google Classroom, so you can definitely use that to help you. So there are a whole bunch of them. A partial list is shown below. It's shown right here. So I'm going to just use this partial list to kind of illustrate what we have to do. Okay. So here is a partial list of Laplace transform. And the complete list is on Google Classroom, so you can definitely look at that. And I already mentioned to you that you're allowed to use that on your tests. Okay? So, here's the some of the basic function that we're going to just use for right now. So the list basically give you the function f, and then the Laplace transform of f. Okay, so basic one will be 1, and that will give 1 over s. So this, well, let me write them out first, and then we can talk about it. So if you have t, then that will be 1 over s squared. And you have t to some power n, that will become that power n factorial over s to the n plus 1 power. So that follows a nice simple pattern. Another very common function that we go do Laplace transform is e to the at. And we're established that that's 1 over s minus a. Essentially, you can think of 1, which is 1 over s minus 0. So therefore, that's technically speaking, 1 is like e to the 0t. What happens if you have a t in front? So that usually indicates like repeated roots. And which is the reason why we have 1 over t s minus a squared. And the last one that we'll write for now is this one, t to the n, e to at, and that would equal to n factorial s minus a to the n plus 1. Notice that these last three formulas actually kind of include the first three, provided that a is 0. Now, one thing interesting about this Laplace transform formula is the following, is that they are actually reversible. Meaning what? Note, these formulas, as well as those on the Google Classrooms, are meant to be used in both directions. What do I mean by that? Meaning that you first use this table from f to L of f when you're rewriting the differential equation into Laplace transform. And then once you completely isolate the Laplace transform of y at the end, you would then use this formula kind of backward to form the solution. What do I mean by that? Meaning the following. Let's say I take one of these formulas. Like let's say, let's number them. Let's say if I take number 1, for instance, the formula number 1 basically says the following. If I do a Laplace transform with the constant 1, I get 1 over s. Implied, this statement can be rewritten into, if I do Laplace inverse of 1 over s, I should get 1. That's what formula number 1 states. Let's look at, I don't know, formula number 4, which is what we have been using for so long. It basically states the following. If I take Laplace transform of e to the at, I get 1 over s minus a. But if I do the inverse Laplace transform 1 over s minus a, that gives me e to the at. Now, show you how this worked in a problem. Okay, suppose I have a function. Let's just use one of these examples right here. Let's see if we can find an example that we can use. Okay, we cannot use this one yet, but let's see. Let's see if we can find one that we can use. This one is good. This one we can use. So let's say we have a Laplace transform. I think we can use this one. Let's see. Hopefully it works out. So example will be following. Let's say we're given that the Laplace transform of y is equal to 9x plus 25 over x plus 3 to the third. And the question will ask you find y. So the first thing you want to do is to rewrite this Laplace transform using partial fraction decomposition. Lucky for us, we know what that is. That will be this. So now what we're basically doing is the following. It's now trying to do y. So what is y? Y would actually equal to the Laplace transform inverse of what we have right here. Now, because Laplace transform is linear, its inverse is also linear. We talk about that back in chapter 3. When you have a function that's linear function, its inverse must also be linear. So therefore, that means that I can now say that's 9 Laplace transform inverse of 1 over x plus 3 squared minus 2 Laplace transform inverse of 1 over x plus 3 to the third. So now it's just a matter of trying to figure out what to do with these two Laplace transform. So if you look at what's on this side and what's on the inside of the Laplace inverse, notice that they kind of look like this right here, like 5 and 6. As a matter of fact, the square look exactly like 5. So we can actually use that. So therefore, we're going to go for it. So I'm going to use this rule right here. So this, oh, actually, maybe I will write it this way. This basically follow this rule. Up to the square. So that's rule number 5. So now all I have to do is just compare this part right here with what's inside the Laplace transform inverse and try to identify what should be A, which, if you think about it, A will be -3. So therefore, this expression right here is actually x minus -3. And therefore, this value is our A, right there. So therefore, that solved that problem. That means this is 9 times t e to the -3t. Now come the next problem. What do I do with this part? So that looked like this formula right here, which I'm going to write down. This right here seemed to me like L of, was that t to the n, e to the at, equal to n factorial, s minus a to the n plus 1. So now all I have to do is just figure out what a is and what n is. So notice that a should be -3. That's easy, because that's just basically what we just did. But since the third power indicator n should be 2, because it's 2 plus 1 power. But there's a problem. The problem is that if n is equal to 2, I should have a 2 factorial on top, which is 2. We don't have that. So what we're going to do is the following, is to fix this. So therefore, I'm going to write this. So this is basically x minus -3 to the 2 plus 1 power. Therefore, we require this to be 2 factorial. But I can't just change the 1 to 2 factorial. That would be wrong, because not the same thing. I could balance it. How do I balance it? By dividing 2 factorial on the outside. So this also go outside on the bottom. So therefore, we balance out my expression. And so what happened to 2 over 2 factorial? It becomes 1. So it becomes just -1. And now this expression now totally fit into our formula. That means now I should have t squared e to -3t as our answer. All right. Unfortunately, my time ran out, so I'm going to have to show you a few more examples in the next video. All right. I'll talk to you guys in the next video. Okay. Bye-bye.